that we might be discussing in the special year. But most of it, they're just these two examples. One is in analysis, one in topology, and which I want to go over in some detail. Okay, so the basic object is these things, arithmetic, locally symmetric spaces. I won't give you a definition just yet, so we'll start off with the basic example. And the basic example is the modular curve. So the modular curve is you take the upper half plane, Poincare upper half plane, so complex numbers with positive imaginary part, and that has an action of fractional linear transformations. Okay, you can act on it by any such transformation ABCD, where that ABCD has determinant 1. Could be real, but you can, inside it we have the group of integer matrices, so SL2Z, which is just a group of integer matrices with determinant 1. And so this is a discrete group, and you can take the quotient. Okay, you can take the quotient of this by this SL2Z, and what I'm going to draw now is a fundamental domain for this quotient. Okay, and it's a picture probably have seen. Okay, so this consists, if anyone can't see this, just shout out. Okay, so this consists of all complex numbers. This is a fundamental domain, and the conditions are z is bigger than 1, and the real part is less than 1/2. So this quotient, it's a Riemann surface that you get by gluing these two sides together and kind of gluing the bottom to itself. All right, so why would you write down this quotient? Probably the most natural way this thing arises is it parameterizes elliptic curves, or not equivalently parameterizes complex tori. All right, so let me just write, if you have a z in this upper half plane, you can make out of it a complex torus. You take the complex plane and you quotient it by the grid you get spanned by 1 and this number z. And these two, so this is now a complex torus. It's a torus, two-dimensional torus with a complex structure. And this two of them are equivalent as Riemann surfaces exactly when the corresponding points are in the same orbit of SL2Z. So this thing is a complex, it's a moduli space. And in that way, it's related to algebraic geometry, but that's something we'll talk about only at the end of the talk. You can forget about the complex structure and just think about its Riemannian structure. So this Poincare upper half plane has a metric of constant negative curvature, which is given by, okay, that's the distance. And so this metric is preserved by fractional linear transformations, so it descends to this quotient. Okay, now this metric, the higher you go up, the closer things are together. So a kind of picture of this, it looks more like, it has some, as it goes up, it gets narrower and narrower. Okay, it's some sort of surface, but it has a long, narrow neck going off to infinity. And in fact, it has only finite area. Okay, it's infinite in this direction, but it has finite area for that metric. Okay, and what I want to do, so the first part of this talk, we'll talk about analysis on this M, and to kind of illustrate how it's special, we're going to compare it with nearby similar spaces that are sort of slightly different. Okay, so first of all, I want a little more flexibility. The type of I want to consider not just this example, but I'll allow myself congruent subgroups of SL2Z. So congruent subgroup means a subgroup that's defined by congruence conditions. So for example, let me write one here. Okay, here's a ABCD where 7 divides C. Okay, it's a subgroup of SL2 of the integers, and it's determined by a congruence constraint. Okay, so the class of spaces we're interested in are things like upper half plane modulo this subgroup. And to see why they're special, we'll contrast it to something which I'll generically denote by m prime, which just means some kind of small perturbation of this. For example, you could perturb the metric a little bit, or you could perturb the group a little bit. You could start with one of these, a group like this one, and then you can deform it slightly, and then its entries will no longer be integral. Okay, so as soon as you do that, it leaves the realm of anything to do with number theory. And so in the first part of this talk, we'll sort of contrast analysis on things like this to these perturbations. In the second part of the talk, we'll do something similar for topology. All right. I think I've just said what's on this. So the basic structure of this talk is, yeah, we'll first talk about some analysis. When we talk about topology, we'll have to go one dimension higher. So I'll explain that when I get to it. And at the very end of the talk, I'll discuss the relationships with algebraic geometry. All right, analysis. So it has this thing. Sorry, are there any questions? All right, so M is one of these, M is a quotient, maybe this quotient or a quotient by one of these slightly smaller subgroups. It has a Riemannian metric, so it has a Laplacian. Okay, and the Laplacian is, this metric is changed from the Euclidean metric by the factor y squared, so the Laplacian is similarly modified. And so you can ask about the spectrum of the Laplacian acting on functions on this space. Okay, maybe it's not obvious you should ask about it, but you can ask it. And it turns out, this is not obvious, and I'll say more about this later, but it turns out that on this upper half modular curve, it has infinitely many eigenvalues, I should have said in L2. Okay, so there are infinitely many eigenfunctions of the Laplacian that lie in L2. And they are spaced as you might expect if, so a priori, there's something subtle about this because it's a non-compact manifold. So you don't, but they behave as if it were compact. That is, as if it were a planar domain or a compact manifold. Their spacing is 4 pi over the area, okay, which is what Weil proved is true in the compact case. Sorry about that. All right, so for example, for the case of the modular curve, this thing up here, the area is pi over 3 with respect to the Riemannian metric, so this mean spacing should be 12. So now people have now gone quite far in computing this. So here are the first 27 eigenvalues after 640,000 computed by Holger Then. And OK, so what do we see from this? I'm not sure. It's a bunch of numbers. OK, at least you can see maybe it's reasonable. There are 27 of them, so the average spacing looks to be about 12. Here's a picture of them. OK, so this is a picture where the x-coordinates are the eigenvalues. I'm sorry. So the x-coordinates of these are these numbers that appear above. Okay, so 1, 8, 56, and so on. All right. Now, there's actually something a little bit unusual about this. Does anyone want to guess what it is before I say it? Yes. Yeah, OK, they clump together. Now, actually, if you take a bunch of, if you just choose numbers in the unit interval uniformly, according to sort of uniformly identically from a uniform distribution, and you plot them, you'll find that they look a lot like this. They clump together. It's a little bit surprising. So in fact, these numbers, if you look at them, they pretty much look as if they were chosen from a uniform distribution. Okay, the clumping, we tend to see that, but it's even if you do it randomly, you find that's true. But in fact, that very fact is quite surprising. Okay, so these look like random numbers, but that's not what one should expect in this setting. Okay, these numbers are eigenvalues of the Laplacian operator. Okay, so if you take the Laplacian on a negatively curved manifold, So this Laplacian, it's some symmetric operator. And if you wanted to make a guess as to how the eigenvalues were distributed, you might take as a model the eigenvalues of a random symmetric matrix. Okay? There are different models of how you would choose random symmetric matrix, but the points we're going to discuss are pretty robust, the same for any sensible model. Okay, so here is, I'm going to now give you a picture of what eigenvalues of a random symmetric matrix look like. So I did this morning for a 1,000 by 1,000 symmetric matrix. And so just contrast this picture with, this is the picture from the previous slide. So this bottom thing is the spectrum of the modular curve. This thing is the spectrum of symmetric matrix, and it's also what you would get for a kind of a generic negatively curved manifold. For example, a small perturbation of this modular curve.
What's GOE?
Oh, yeah, it's the Gaussian orthogonal ensemble. It doesn't matter. Sorry, I should have deleted it. It's a specific model of random symmetric matrix, but it's not, for the purpose, it's not relevant which one we. Yeah, sorry. Okay, I screwed. The dot sizes are meant to be the same. Okay, so so this thing, this is discovered by people who are thinking about quantum chaos. And it's a very surprising fact, then, that this modular curve differs from what you would expect. There's another point on this slide, and I can't remember what it is. Let me find out. OK, there, yeah. OK, yeah. So this is referring to eigenvalue. If you take eigenvalues of a symmetric matrix, the sort of most obvious thing which comes out to you among the many interesting features is that they repel each other. So in other words, if you take, imagine if you were taking points at random with average spacing 1, the chance of having two of them in an interval of length epsilon is epsilon squared. But for eigenvalues of a symmetric matrix, that's epsilon cubed. Okay, and the chance of having k of them, again, k eigenvalues in that small interval is epsilon to the k plus 1 over 2. I'll just write that here because it'll come back later. Okay, and a very, just a heuristic as to why is that for a symmetric matrix, the condition that two eigenvalues coincide is a codimension 2 condition. It's not a proof, but it's something heuristic for why that should be the case. So it's a smaller set than you would imagine when two eigenvalues come together. OK, so that's what's surprising about the spectrum. Actually, I have one more thing to say about the spectrum. Are there any questions? Yeah.
Do we know something about the eigenfunctions, how spread out they are in some way?
So right, there's a lot of study about how you might expect them to behave like random superpositions of waves, and maybe they don't for this specific case. So there's a lot of study of it. Sorry, this is just the very first thing. Right. Yeah, but again, you'll see that reflected at the level of functions as well, the difference. OK, there's another point which I didn't emphasize at first, which is that it's surprising that there are eigenvalues at all. OK? So it is not at all obvious that there exist Laplacian eigenfunctions in L2, and this was proved by Selberg. And he did this with the trace formula. OK, and he did this, the proof is specific to these modular curves or these congruent subgroups. And the reason is that in the trace formula, when he analyzes the continuous spectrum, it's related to the properties of the Riemann zeta function. And he uses specific analytic features of the Riemann zeta function. Okay? So now if you perturb it, the proof doesn't work. Okay? If you change the group a little bit, if you change the metric a little bit. And I believe that it was, however, I think people thought it was just maybe a peculiarity of the proof until the work of Phillips and Sarnak in the 1980s, which more or less convincingly showed, it's not a full proof, but it's clear after this paper that, in fact, a generic perturbation of this situation will have no discrete spectrum. Okay, so the existence of discrete spectrum is something that you shouldn't expect. The non-compactness really So the problem is, okay, the problem is that the continuous spectrum has this strong tendency to absorb the discrete spectrum. But this doesn't seem to happen in the arithmetic case. Okay, so that's also the very fact there are eigenvalues, let alone that we can talk about the Weil law, is surprising.
So the Laplacian is, so the perturbed K to Laplacian is still self-joint?
Yes, yeah.
Manifold, right?
Yeah. You could just take the same group, and you could change one of these, perturb one of the groups a little bit. So all the sort of gross features are the same.
So it's self-joint, but there's no displacement.
Yes.
Actually, for compact arithmetic, do you still have, it looks like GOE, or it looks?
I would assume it looks Poissonian. I don't know. I don't know of any data off the top of my head. But Peter, is that?
They experimented with triangles, arithmetic triangles,
Yeah.
which are compact.
And they found Poissonian for the Arth. Yeah.
All 84 arithmetic triangles.
Ah.
As Madame Vigneras explained to Bogomolny.
Bogomolny has some argument to explain why it's possible.
There's many heuristical.
One of which I'm about to give. One of which I'm about to give. Okay, so why should this be the case? And I think some way or the other, the only sensible reason is this class of things we're considering has a large class of extra symmetries. All right, so before I say anything specific, they're called Hecky operators, and before we say anything more specific about them, whatever they are, they give you some, they are going to give us some endomorphisms of L2. I'll tell you what they are in a second, and these commute with the Laplacian. Okay, so now in the previous discussion about GOE, or that this should have a spectrum of symmetric matrix, the point is this Laplacian for these arithmetic surfaces is very constrained by the fact that it commutes with all these t. Okay, so if you imagine taking this t and diagonalizing it, then the Laplacian has to commute with it. It's more like choosing a random diagonal matrix than choosing a random symmetric matrix. Okay, so roughly speaking, you can say the Laplacian, the existence of these, normally the eigenvalues repel each other. Being forced to commute with this reduces the influence of one eigenspace on another. Okay, and the same thing, so might be what so that, for one thing, it kills the repulsion. And speaking in it heuristically, again, as far as discrete spectrum and continuous spectrum, it kind of separates the influence of the continuous spectrum from the discrete spectrum. Okay, it sort of breaks apart all the eigenspaces. So I'll tell you now, I'll say what these Hecky operators are. The exact details are not important, so I'll just write what they are so that you can see that they're defined in some concrete and simple way, but you don't have to pay attention to the specifics. All right, maybe I'll write this on the other side. Okay, so on the upper half plane, we can consider the map which multiplies by p. Okay, so here p is a prime number. Okay, it doesn't really have to be prime, but it's the way I set it up, it's going to be prime. Okay, so we can look at this map, and this map is the same as acting by the fractional linear transformation p0, 0, 1. Okay. Now, this guy, right, so I would like to kind of say this thing descends to this quotient down here. This matrix doesn't normalize SL2 of the integers. If it normalized it, then it would fit into this picture here. But it almost normalizes it, okay, meaning that if you apply it to SL2 of the integers, you get another group which differs from itself only by finite index. So what that translates into is you can descend it to a kind of multi-valued. So here's what you do. You take a thing in here. You take all possible lifts up to here, apply this, and go down. But you only get finitely many possibilities for the image. OK, so right. So what this Hecky operator, yeah, you should just remember it's indexed by prime numbers. OK, it takes in a point and it spits out p plus 1 points. And if you move the point z by a small amount, each one of these points move by the same amount. Okay, so each branch of it is isometric. So it's not a physical isometry, but it acts on it acts on things to do with the manifold. So for example, if you have a function on this manifold, you can act on it by just adding up the values at those points.
Asymmetric, so is this supposed to scale the metric?
No, it's literally isometric. It's literally isometric. Yeah. Okay. Yeah. Any other questions? All right. So now I don't want to define. It's to give you an exact definition of this is sort of painful, but I'll give you a sense of what the general concept looks like. We're going to work with this in one other example. So, all right, this is the example we discussed. Upper half plane modulo a congruent subgroup of SL2 of the integers. Now, roughly speaking, you can generalize this by replacing the role of SL2 by any semi-simple group and the role of the integers by any integer ring. Okay, so the sort of example one dimension above, the natural example, are if I replace SL2 of the integers by SL2 of the Gaussian integers, this acts on hyperbolic 3 space, and you can form a 3-dimensional manifold. So let me just, again. Right, so you can do exactly the same thing, replacing the role of the integers by the Gaussian integers. Okay, so I squared is -1. This now acts on hyperbolic 3 space. So now this is triples, x1, x2, and y. And that it has this thing has no complex structure, but it does have a constant curvature Riemannian metric. Okay, so the whole discussion that we had to date, we could have again with this one, and it would look rather similar. So more generally, if you have an arithmetic subgroup of a semi-simple Lie group, so I won't define that, but for example, you can take matrix group SLN over the integers, or symplectic groups over the integers, or subgroups of those defined by congruence conditions. Those always act on some canonical Riemannian geometry. Okay? So for SL2Z, that was the upper half plane. For SLNZ, for example, it's the space of positive definite symmetric matrices of determinant 1, which you can give a Riemannian structure, invariant Riemannian structure. And then the general definition of arithmetic locally symmetric space is you could take a quotient of this symmetric space by that group gamma. Okay, so there's one for for every, or there's a whole collection of these for each semi-simple group over the rational numbers. So there are many interesting spaces that arise this way. Okay, but for the rest, I'm just going to focus on this second example that I wrote here. Okay, this hyperbolic 3 space mod SL2 over the Gaussian integers, just to keep it easy to visualize. Yeah. Okay. So the next part of the talk, I'm going to talk about topology. And so the points that I'm going to make, I can't make for 2-dimensional hyperbolic space, so I'm increasing the dimension by 1. So otherwise, everything is very similar. So now, where I had SL2Z, wherever you have Z, you have Gaussian integers. And this quotient is called a Bianchi manifold. It was studied by Bianchi. So here's Bianchi's paper, I think, from the late 19th century. And this is part of the thing where he's actually constructing a fundamental domain for this group SL2 of the Gaussian integers. Okay, this is the hyperbolic 3 space viewed from above, and he's constructing a fundamental domain that's a little bit analogous to the one that I drew on the board, but in 3 dimensions. Okay, so here you cannot by a theorem of Mostau, you cannot deform a group like this, which in the case of hyperbolic 3 manifolds. But what I want to do is I'll compare the topology of this quotient, hyperbolic 3 space mod congruent subgroups of this, with general hyperbolic 3 manifolds. Okay, so a general hyperbolic 3 manifold looks like the quotient of hyperbolic 3 space by some subgroup. It's a subgroup of SL2 over the complex numbers, but it's not arithmetic. It has no, I won't define that, but it's not defined simply in terms of a matrix group and a ring of integers in that way. So I'm going to contrast the topology of the arithmetic and non-arithmetic ones, and you'll see there's quite a nice parallel with the situation with analysis. Okay, so the simplest, right, so now gamma is now something contained in here. The simplest topological invariant we can look at is the first homology of this. Okay, and the first homology, because this is contractible, is just the abelianization of this group gamma. Okay, the group gamma made abelian. So this was, it's been, well, Bianchi had already effectively written down presentations for these groups in some simple cases, so he could certainly knew what this was there. But the first systematic computations that I know of for subgroups of Bianchi groups were by Elstrud, Menneke, and Grunewald, and these were taken further by Grunewald and Schwärmer. And so what they did is they computed the which family of okay. So let me just define what family of subgroups they looked at. So this is called gamma naught of n. Is this subgroup where n divides the lower right entry. And unfortunately, these early computations, I think Elstrud, Menneke, and Grunewald were in the 70s, didn't go far enough to kind of, I think it's not so easy computationally. They didn't go far enough to see the interesting phenomena start. So I'll give you some more recent computations. These were shown by Mike Lipnowski in his talk last week, but I'll repeat them. So, all right, these are abelianizations of subgroups of SL2 over the Gaussian integers. And what happens is, all right, so as I said, gamma naught n, this notation means that n divides the lower left entry. As soon as this n reaches a certain threshold in size, this first homology becomes very large. Okay, and it starts to grow very rapidly. Okay, so by this stage you have the torsion part has size about 10 to the 300. These examples aren't kind of carefully picked. Okay, it's generic behavior. You choose a large n, and this is what you'll see. Okay, so these, are there any questions?
Yes, so these are prime ideas?
These are, no, I don't think they're prime idea. Oh, I don't know, I can't factor it in my head. So let's, the first one is prime. That's all I can I think they're prime. But there's no special, as far as this phenomena is concerned, primes are not special.
And just out of curiosity,
yeah.
Second line, there's a question mark after the 6. Is there a missing digit? Or
No, I think it was something about, I don't remember what it was, but there was something about the 2 torsion I wasn't sure of. Yeah, it's
I think Laurent's question is relevant because otherwise you might see a bigger rank there from lifted guys, right?
Sorry? What did you say?
You worry about lifted guys, so that's probably prime. Split or non-split.
But as far as the feature of large torsion, you'd see it whether or not it was prime. All right, so again, I want to compare this to some nearby situation to see if it's interesting. So yeah, these computations that I just showed you were actually in response to a conjecture that Nicolas Bourgeon and I made a few years ago that the torsion, okay, we made this conjecture about arithmetic hyperbolic 3 manifolds. Okay, not about general. We went about arithmetic ones, and I'll show you some picture about that in a second. But we conjectured that for arithmetic hyperbolic 3 manifolds, the torsion should grow exponentially with the volume at this specific rate. Okay, and we could prove some kind of analogs of this in slightly different situations. But anyway, this is still a conjecture, and it seems to be quite subtle to prove. And what I want to show you is, again, to contrast it in the arithmetic and non-arithmetic case. And so the picture I'll show you are from computations by Jeff Brock and Nathan Dunfield a few years ago, maybe about 2014. Okay, I'm sorry. Before I show you the picture, what the picture will show is the ratio of this homology. It'll show this ratio times 6 pi. In other words, the thing which is supposed to converge to 1 as the volume gets large.
Where is 6 pi coming?
6 pi comes from some computation of L2 torsion on the universal cover. So it's something it's something you can understand. All right, the top is the notation. So each of these dots corresponds to some hyperbolic 3 manifold. Top are arithmetic, the bottom are not. Okay. Blue and red. So blue dot. Well, blue dots are where the first Betti number is 0. That is the first Betti number with rational coefficients. Okay. So blue dots are where this homology, this group is a finite group, and red dots are where it's infinite. It has a free part. Okay. So here's what you see. In the arithmetic case, there are a lot of red dots and a lot of blue dots, and they more or less converge nicely. In the non-arithmetic case, there's no problem with the blue dots, but there are these red dots that behave much more problematically. Okay? And actually, the situation is very similar. In this group, okay, there's a kind of battle between the torsion part and the free part. Okay, when there's a free part, the okay, so when this thing has when this group has a free part and a torsion part, they kind of battle with each other. Okay, so this is what is happening here. These red dots is when the group has a free part, and the free part is kind of sucked up all the size and reduced to size the torsion part. What happens in the arithmetic case is the same kind of phenomena that happened before, which is that the Hecky operators seem to have the effect of isolating this free part from the torsion part. Okay, I think of it as an analog of isolating the continuous spectrum from the discrete spectrum. So you'll see, by the way, certainly most of the time, even in the non-arithmetic case, this is still true. But there's a real problem. I don't know if it's proved that it fails in the non-arithmetic case, but you can see at least it certainly behaves differently.
So where the red and the blue again?
Yeah, sorry. Blue means that this group is torsion, the first, and red means that it has a free part. So it's and the problem, the case where the thing is subtle is exactly when it has a free part, because it interferes with the torsion group.
Some of the red dots are inside the blues. Are those with rank 1 or something?
No. It's just there's so many blue dots that, in other words, in the non-arithmetic case, positive rank is very rare.
But some positive rank guys still look like they're near 1?
Oh, yeah, yes, some of them do. That's right. Yeah, I don't know this conjecture. All this says, I think it shows that it behaves differently. I'm not.
Are the ones that are far off rank 2 or something? Or?
I think these actually have rather high rank. Yeah. I never looked at why that is, but I think they have high rank. But that's also true in the arithmetic case. Some of them have high rank, but it doesn't have the same damage. Sorry, Richard. Yeah.
I can't see the second. So there are a lot of red dots off for small volume. But
Yes.
high volume, there are not many. But I can't see whether there are any red dots for high volume, or whether the red dots are they all on top of the blue?
Which one are we looking? Above or below?
Below.
Below. This is the last red dot out here.
And there are no red dots.
There are no red dots past that.
So why is
So maybe
so
the
for high volume you're unlikely to have a
That's right. So the non-arithmetic cases they're much less likely to have free path. Or when they do have it, it seems to affect the situation much more. And it's that affecting of one or the other the Hecky operators inhibit.
Is there a topological reason for that?
I think there is, but I'm embarrassed to say I never looked into it. You're asking, I'm sorry, what topological reason for what?
For the fact that there is no red on the right?
Well, I think it's more like in this case, there's lots of red for number theoretic reasons. But on random grounds, on random grounds, I think you would expect positive Betti number to be rather rare. And in the arithmetic case, it's applied for base change. But yeah, so the main, okay. The only point I want to make with this diagram is that they look rather different. Any other questions? Okay. There's also kind of a very pleasant parallel here to the repulsion of eigenvalues that you see in the analytic case. There's a paper by Dunfield and Thurston where they study a model of random hyperbolic three manifolds. Okay, so they specify some way to create a class of hyperbolic three manifolds, which they call random. These are almost always non-arithmetic. Okay, so you can think of this some way of generating generic hyperbolic three manifolds. And one thing they show is that, the P rank. So they compute actually the dimension of the mod P homology. I should have said Z mod P here. And so to speak, factors of Z mod P repel each other. So what they show is that the chance of having a Z mod P to the K is P to the minus K plus 1 over 2. Okay? Now, this is the same exponent as for the eigenvalue problem, and it happens for the same reason. Okay, it's again, I'll say a little more about this in the next slide, but it comes again from the studying random matrices now mod P. Okay, so the exponent has exactly the same source. And again, this is something which I don't think anyone has actually studied this systematically, but just when I glance at data, it seems to me very unlikely this is true in the arithmetic case. Okay, so this first thing is an analog of repulsion of eigenvalues. In the arithmetic case, you certainly see larger rank much more often. Okay, I'm not, as I said, I haven't done any statistical tests, but it looks like it again separates.
What about Z mod P to the KC?
Yeah, you could do the same for exactly this. There would be some different exponent, but the point is, again, it's controlled by some random matrices modulo that power of P. So I'll just, just to summarize the two things I've said, both the analysis as far as eigenvalues and topology are controlled by some linear map. Okay, the eigenvalues are controlled by the Laplacian. The homology is controlled by the differential in some chain complex. Okay, and the naive thing to do would be to model those as random linear maps, and that corresponds to this prediction, GOE prediction about eigenvalues of the Laplacian, or this Dunfield Thurston prediction about topology. But when you have Hecky operators, everything is forced to commute with the Hecky operators, and it makes these models collapse. Okay, so these arithmetic manifolds behave in this very kind of rigid and strange way because of all of these extra symmetries. Okay, so last part of the talk is about the relation of these with algebraic geometry. Are there any questions before I go to that? Yeah.
So there are maybe two other models of random arithmetic algebraic manifolds. One is for the things which fiber over a circle, right, rhythm.
Yeah.
And another is the one which you can have those geodesics from a sphere bundle. You know the sort of similar questions for those models?
So I think the circle one would behave the same. Maybe not the exact same, but definitely as far as the exponents that I said. I don't know about the other one. I've never thought about it, so I don't.
Big ribbon, that's fine.
Okay. So I've tried to show you things about these spaces that are quite visible, but to go a little bit deeper, you have to think about the relationship to algebraic geometry. So that's the last few minutes of the talk. So we're going to go back. I'm still going to stick to the two classes of example spaces I had. So let's go back to the modular curve, hyperbolic plane modulo SL2 of the integers. And as I said, I mentioned at the very start, this is a moduli space for complex tori. Okay? So it has a complex structure. And by using this moduli property, you can give it, in a natural way, the structure of an algebraic variety, an algebraic curve over the rational numbers. Okay? Meaning there's a natural way to think of it as the set of complex solutions to some system of equations inside projective space over the rational numbers. Okay, so this comes from, as I said, thinking about moduli of elliptic curves. And the kind of starting point of the whole, or at least from my point of view, the starting point of the Langlands program is a theorem of Eichler and Shimura, which says that this algebraic structure of this thing has something to do with Hecky operators. Okay, so I'll state some form of this theorem from the 1950s. So what it says is the number, okay, you have this now an algebraic variety. So at least for all but finitely many, this cut out by some equations with rational coefficients. So apart from some finite number of exceptions, you can count how many solutions it has mod p. Okay, it's a sensible question to ask. And Eichler and Shimura showed that that number is essentially the trace of the pth Hecky operator. So I didn't say this explicitly when I was, where are my Hecky operators? These guys, not only do they act on functions, but they also act on homology and cohomology. Okay, so you have a cycle here, and you just apply this multi-valued function to it, and you get another cycle. So it acts on everything, and you can ask about its trace. So this is a wonderful thing, because this side is almost in the realm, you could define it just with group theory, and this involves some algebraics, some structure of algebraic geometry. Okay. So let me say one thing about this. So one way you can sort of try to go about proving it is you can compute this by some Lefschetz number. Okay, so you can try to find the fixed points of this multi-valued function, and then you can see how those fixed points relate to points on this x mod p. That's one way you could, if someone told you it's true, you can go about checking it that way. So another way to write this is that this p plus 1 here is the number of points on the projective line, mod p. So I can rewrite this in this funny way. Number of points, I'll think of 2 copies of p1, subtract 2 copies of x. I'm thinking of this some sort of virtual linear combination of varieties is the trace of this TP. So the only reason I write it that way is to say that there's a natural context where you can take this sort of thing, and that's the theory of pure motives. Okay, so the theory of pure motives is some larger, it's an abelianization of the category of varieties, and it allows you to take things, make sense of combinations like this. And following on this, there's a large body of work that in these arithmetic locally symmetric spaces that happen to have complex structures, these are called Shimura varieties, you can understand the relation between traces of Hecky operators and these motives. Okay, there's been an enormous amount of progress made on understanding how to generalize this statement. Okay, now I'm going to go to the Bianchi case. Okay, and here, exactly the conjecture is that exactly the same thing is true. Okay, so in other words, M is now the quotient of this hyperbolic 3 space by a congruent subgroup of SL2 C of the integers. And then it's going to be exactly the same conjecture. All right, where I've said the word motive, but you could think that this can be a virtual linear combination of varieties. Okay, there's no need. And other than that, it's the same conjecture. There's one of those such that the number of points over FP is the trace of the Hecky operator. So I've said this is still more remarkable, and the reason is, well, for one thing, we can't prove this, but this thing has no obvious relation to algebraic geometry. It's a Riemannian three-manifold, and there's no obvious way to get. On the previous slide, the x is sort of given to you. It comes from thinking about the manifold as a complex analytic manifold, and you make it descend it to an algebraic variety over the rational numbers. Here, there's no candidate for what this should be. Okay, there's no candidate. So we think this is true. The strongest evidence for this is a theorem that was proved independently by Harris, Land, Taylor, Thorne, and Schulze, which says that this statement is true modulo L to the n. In other words, if you have a prime power, you can find a variety x, maybe depending on the prime power, such that this equality holds modulo that. But it might be a different, and probably will be a different one for each prime power. Okay, so this is something which is very mysterious. I'll just say, one of many reasons why it's so slippery is this right-hand side. You can't access it anymore by Lefschetz number. If you take the alternating sum of traces of this Hecky operator, you get more or less 0 because Poincare duality makes the contributions of H1 and H2 cancel. Okay, ignoring some minor issues of the boundary. What do I do? Well, oh, sorry, in this statement it's rational. In this statement it's rational. Yes, I'm ignoring all the torsion for this. Yeah, it's a fair point. Yes. No. Right. To make this as straightforward as possible, I'm ignoring the torsion. I mean, it's not false what I wrote, but I'm not. Yeah, I'm not saying how you should upgrade this for torsion. Okay, so this is where I don't think we have any at present any really convincing ideas of how we should produce this x. So this case remains much more mysterious. Okay, are there any questions?
There are special cases where you can find it or not?
Yes, yes, you can special cases where you can verify it. Yes.
Some of these were found by Grunewald's Minica.
Yes.
In numerics, they found certain elliptic curves.
Yeah.
Very numbered as well.
Yeah, I mean, the experimental evidence for this is very good. It's not most cases where it seems feasible, where we could guess numerically, we should be able to find it by search. We find it.
Actually, the way they wrote it, if you remember in the paper, they say, well, they don't really understand what Langlands is saying, but maybe Langlands has got something to do with it.
Okay. On the last slide, I'll just say a little bit of things which are related to what I've been thinking about and which will be, I think, discussed in various ways in this special program. So, Shimura varieties. Shimura varieties are things like this upper half plane mod gamma. They're arithmetic locally symmetric spaces that happen to have the structure of complex varieties. So these are very well understood. Okay, no, that's strong. That's strong. These are they're much better understood than general symmetrics. Okay, so the general examples of spaces like this, for example, the one for SLN over the integers if n is bigger than 2, look more like this Bianchi orbifold. They don't have any obvious relation to algebraic geometry. But these general type of spaces actually, they exhibit, although we don't understand them, they seem to exhibit some richer structures than the Shimura case. So I'll just say briefly what these are, and then I'll stop. I already mentioned that the trace of in this Bianchi case, the trace of the Hecky operator on H1 and H2 is essentially the same because of Poincare duality. Turns out that Poincare duality is not really a very good explanation for this because one finds the same phenomenon happening on other locally symmetric spaces in degrees that are not complementary. Okay. So you have this situation of these two cohomological degrees, and the Hecky operator has exactly the same eigenvalues in both of them. So in that situation, if you have two spaces with an operator with the same spectrum, you would like to have some isomorphism that explains that. Okay. So you can construct this, and you can do it by making sort of deriving the Hecky operator. So there's a derived version of the Hecky algebra that you can make. It's not interesting for Shimura varieties, but in cases like this Bianchi manifold, it gives you a way to pass between cohomological degrees. Okay, and it kind of explains, separate from Poincare duality, and better why these have the same trace. Once you have this structure, then the Langland's program, which relates Hecky operators and things like Galois representations, leads you to look for the same structure in other places. And so I'm sorry, these last couple of points are a little bit technical, but in the Langland's program, we study some kind of moduli space of Galois representations. Corresponding to this existence of derived Hecky operators, that moduli space itself, in this, when you're studying these Bianchi manifolds, you have to consider a derived version of it, meaning that it's sort of naturally, the ring of functions on it is something like a simplicial ring. And that's because these Galois representations are, their deformation theory is obstructed. And these two things are kind of reflections of what I think is the deepest thing, which is that I think there are many indications this manifolds of this Bianchi type are naturally related not just to pure motives, but to mixed motives. So the pure motives I mentioned earlier are a kind of semi-simple version of a subtler object called mixed motives. And one of the things I hope to understand this year is better how these mixed motives are related to the cohomology of these arithmetic groups. So I'll just say one last thing about this point D, which is that it's not, there's one case of it which has been around for a very long time. If you look at the algebraic K theory of the integers, so the algebraic K theory of the integers is related to mixed Tate motives. It computes something about mixed Tate motives, and this, by definition, shows itself in the homology of SLNZ. So the content of the statement D is that actually it's not just mixed Tate motives that you see in this SLNZ, but you see much more interesting extensions of much more interesting motives as well, but not in the stable homology. You have to look further. So okay, so these are so this sort of theme D, Sasha Goncharov is giving some lectures on it, and I will give some lectures on it later in the year, and then Ramyar Sharifi will talk a bit about it. So if you're interested in this, you can come to our seminar. Okay, thanks.